So there are two broad things we'll be talking about today. When we talk about urban drainage encompasses two broad design areas. On one hand, you have SEWER design. You can call it SEWER, you can call it foul SEWER, you can call it sanitary SEWER. There are different names. You can call it sewage. They all mean the same thing. These are the wastewater coming from the household by virtue of human activity, by virtue of the intake of water, by the virtue of using public water, then you have to discharge public water. So that is the sewage. It comes from your bedrooms, it comes from your kitchen, it comes from your washing, it comes from the household activity. That is SEWER or foul SEWER design. The other one is the STORMWATER design or storm SEWER. And when we say storm SEWER, we are referring to those water coming from hydrology, coming from precipitation, coming from natural events, rainfall, the hydraulic cycle. So when these water come, it's expected that you need to design for them and then channel them to the open stream or open water body. In some cases, you need to design a retention basin. In some cases, you need to design an infiltration basin, two different words, infiltration basin or swells. Then you can also design what we call combined sewer overflows, whereby you retain this huge quantity of water and then discharge them gradually. So you could see we have storm on one hand and we have SEWER on the other hand. So when it comes, the same principle of engineering is what is involved, right? And that principle is what we all know, and we've been talking about it in the last couple of weeks, that Q is equal to area times velocity. That has always been it. We now said that because you don't use all the areas, you use what we call paved areas. It is not all the areas that contributes to runoff, that contributes to discharge. And every area have a different parameterization. Grass can absorb, open field, for instance, will absorb more water than where you use, let's say, paved area. So it means that we need to introduce a constant called C or coefficient. So that becomes C. Since we're talking about precipitation, we now have I as in intensity, and we have A. So where C is the coefficient of runoff, I becomes rainfall intensity. Right? Then A, you don't just say area, but you say area of catchment. Area of catchment, that's the technical word. Now, all this is for storm, or the one we call drainage. People say drainage. Then when it comes to the broader, which is SEWER, right? And I've said you can use that word interchangeably. In other words, you can You can call it foul sewer. You can call it sewage. You can call it wastewater. Oh, that's a cool one. Wastewater flow. When I say wastewater, people might not really get it until you say wastewater flow. Then there could be other names. In engineering, they classify it as sanitary engineering. The design of it is called sanitary or sanitary system, whatever. I mean, these words are used interchangeably. So now, in that case, the same law of continuity or law of fluid dynamics applies, which is Q times V. But in his own case, the individual parameter starts to change. The individual parameter starts to change. And instead of, we can have your CIA, right? But in this case, C will mean a different thing. Instead of saying, instead of saying I, you will rather use small q, which is like wastewater flow. Then you multiply it by A. But in this case, your A is now area of pipe, cross-sectional area of pipe. So your A now, your C becomes, we call it peak. Peak flow, peak wastewater flow. Yeah? Or peak, in case of what we did last time, we call it peak demand. So let's call it peak discharge, because it's no longer a demand, but it's now a discharge. Peak discharge, or you call it, it's just like a safety factor. Small q will now be your wastewater flow. Remember, flow is the same as discharge. Don't forget that, please. And what else we have there? We now have A. Our A becomes, depending on what you are doing now, A will become the cross-sectional area section of our put pipe, but it's not only pipe, it could also be member. Because if you are using a trapezoidal system, or if you're using open channel, then, or rectangular open channel, for instance, then you know what we are talking about. So this now becomes the area. So I wanted to point out the difference. This system does not have how to change the color. So you could see that engineering is engineering. So it's the same thing. These two are the same. There's no difference. The only difference is that when it comes to this place, I'll be looking for precipitation data. And when I'm looking for this place, I'll be looking for the area of the catchment, the area of the city, the area of the estate, the riparian area that the runoff is coming from. So it's going to be like a surface thing. It's going to be like a spatial thing. Spatial thing. But when it comes to sewer, then that area becomes the throttle area, the size, pipe size, which of course is the cross section, because pi r square is the cross section. I mean, we all know how the mathematics now goes from that end. While Q is no longer the I, rather it's now the quantity of flow. And let me give you one tip. What you we normally say that garbage in is garbage out, right? What it means is that if you want to understand what you produce as a wastewater, you don't need to do anything. All you need to do is to take a look at what you are consuming. In the Western world, nobody comes to measure your wastewater. What they do is that as they're giving you drinking water, they are charging you simultaneously for wastewater. Because come to think about it, where will the water you are discharging go to? And are you going to produce more than what you are given? No. So invariably, if I supply you 20 cubic meters of water and you use it in your house in a month, technically, I should expect you to produce wastewater that is worth 20 cubic meters of water. So that is simply where you get the value from. So you don't need to crack your head about it. So when we come to that place, we'll be using that individual water demand. That's individual water demand requirement. Right? Okay. Now, that is where we are now. So let's go back to our folder. Any question? So that is what you have in the folder called Nigerian Code of Practice. Nigerian Code of Practice for drainage. So that's a tool. It's a reference code for the sewer and stormwater sector. And I can tell you, they did a good job. Now, we'll be starting 3 things we're looking at today. Let me put them inside one folder so that it will be understandable. We'll be looking at hydrology. We'll be looking at hydraulics. And we'll be looking at general sanitary sewer design. So 1, hydraulics. 2, hydrology. 3, sanitary design. So if you are downloading the material, you can just organize them in this way, so to make more sense for you. The other thing is exercise that we'll do using rational method. So for the rational method, we have the material here for rational method. I'll put inside this one. Then we have the Excel charts. No, ignore this. This is just further reading. But let me still put it there. Then we have the charts. How you do your charts, your calculation sheets for rational method. Then the other 2 are the solved solutions. So I think let's just stop from there. Let's stop there for now. So go to the folder called rational method. If you've done that, but your own should be exposed. Where's my hydraulics? Okay, no. Let's go to course material. So today I'll be laying the foundation. Maybe from next week, we'll go into the calculation. But once in a while, I'll do a little bit of a calculation. So let's look at the sanitary design. Or will I say, let's look at the hydrology. Let's start from hydrology. Where is water coming from? And how does it work? So wastewater collection and discharge. We have 2 systems of wastewater. We have sanitary sewer, which I've tried to explain, and the stormwater sewer. In rare cases, you have the combined system. The combined system usually comes in where you don't have space. Let's say for places like New York, New Jersey, and Heathrow, or Los Angeles Airport, all these places that you don't have space anymore, you can decide to combine the stormwater and the sanitary sewer using very special technology and special separation systems. In fact, special automation and monitoring, because it's not easy to use the same pipe where the wastewater will flow and then storm water will also flow. It's not very easy. Now, okay, somebody has to share the link to the folder again. Okay. Done. Good. For the separate system, it comprises two discharges. The first discharge is what we call dry weather flow, DW. Dry weather flow is the sewage flow when there's no rainfall. Speaking like a local man. But if I want to speak technically, I'll say that dry weather flow is that flow in the system when there is no storm event. So if there's no rainfall, if there's nothing, the wastewater flow in the pipe will correctly capture what is coming from the toilet, from the bedroom, from the kitchen and everything. That becomes the real base flow. However, because of groundwater flow, because of what we call parasite water, you need to introduce this QR called runoff added. It's like a safety factor added to dry water flow. So here we call it unavoidable storm inflow into the sanitary sewer. We expect that in as much as your pipe is laid on the ground, there will be parasite water. This happens frequently, especially in a place like Abuja. In Abuja, once there is flow, if you go to the treatment plant, you find out that discharge will increase because there's infiltration water. There are waters that just find their way into the sewer, either from ground, from breakage, from pipe burst, or from any other way. So you must factor in those common, often looked down discharge that are coming. So that's what you do. But to make it easy, there's just a value for it, a fixed value for it. So I want you to consider this as an added safety factor. Engineers, we know that anything we are doing, we're always dealing with safety factor to take care of some contingencies or to take care of some things that we didn't provide for. Then, for the storm sewer, the sewer is simply QR, the stormwater flow. It does not require any other safety factor. It does not require any additional safety factor because it's basically when rain is falling, when there's storm events, you don't expect water to come from another source. The water that is coming is just the water that is coming. There's no safety factor in this one. There's no added whatever. In this case, it's just the safety factor that you have there. Good. Then for the combined sewer overflow, it could be sanitary plus stormwater. But don't even talk about it because it virtually doesn't exist in our climate. So this is the urban drainage system, generally, talking about runoff, right? You have precipitation, you have snow, you have hail. Then when they fall to the ground, they start formation of runoff. And the formation of runoff takes place after there's wetting, evapotranspiration, depression storage, infiltration runoff, and then drainage. Then after that, you now have the one that's left, and that becomes your stormwater. So you could see that once it fails, one rain comes, some will wet the ground, wet the leaves, wet everywhere. That's part of losses. Then evapotranspiration, the plant will absorb some and give out some. Then there's depression storage. Water will first depress. And then finally, you have the one that will flow to your drain system. Okay. Now, that is that. So let's continue. Now, let me give us some variables and parameters that we'll be experiencing in the course of our design system. Number one is what we call what do I call it again? Duration for the stormwater. Now let's focus on stormwater first. For the stormwater, you have duration. So you have the height or depth. The duration is measured in minutes or hour or seconds. Then you have the rainfall depth. The rainfall depth, assuming you're measuring the rain gauge, is the rainfall depth. Then your intensity becomes your depth over your duration, which is millimeter over meter. And it's a dimensionless constant. But we need to provide dimension so that somebody will know the spatial extent or the temporary extent. Then we have frequency. We have frequency. We have frequency. Frequency is that we don't expect the same amount of rainfall every day. We don't expect the same level of intensity. So there's this set value, or let me say there's this recommended value that you should use, and that's what we call probable maximum flood, or probably storm event, or the storm with the highest frequency. Frequency is probability. At what probability will this rain occur every year? Because in design, you use the maximum, the worst case scenario. But it's not every day that we experience worst case scenario. So now you must have a representative value that you now use. So you can say 20 years flood, 10 years flood, right? 5 years flood. Those things are in terms of their return period. But frequency is simply the inverse of the return period. Frequency is a reverse, is inverse of the return period. So if we are saying that this storm will fall once in a year, it means that the frequency is 1 over 1, it becomes 1. If we say we expect this storm to take place once in 2 years, the return period becomes 2 years. Therefore, the frequency becomes 1 over 2 or 0.5. If we say, like I'm designing for flood does not occur every year. So I'm going to use what I call the 10 years flood event. So when I now say the 10 years flood event, I'm now saying what rain will come at least once in 10 years. In other words, I'm designing for that worst case scenario that can happen 1 in 10 years. So the frequency becomes 1 over 10. It means it can only occur once in 10 years. So one thing about stormwater design is that the higher the frequency, the higher the cost, the higher the return period. That's why if you're designing for normal storm events, normal drainage, you don't use more than 5 years. You just use 1 or 2 years, meaning that the frequency is higher. But when we start using 1 over 25, 1 over 25 is about 0.2. Yeah, about that, or 0.4, 0.2. So you find out that 0.4, sorry. So you find out that that is now a lower frequency, and that will lead to a higher return period. So this A now means the annum return period. Yn becomes the frequency. Why do you need the frequency? You need it because what Mr. A is designing could not be what Mr. B is designing. Let me give us a practical example. In Asaba, I have my friend, Jirajon Anwalo, Jeff Con Associates. He designed the Asaba drainage system because of the incidence of rain in Asaba, close to the Asaba town, close to the government house. He designed for 25 years. When he designed for 25 years, he was getting drain size, stormwater drain of 3 meter by 3 meter. And when he presented it, it became a problem. People were questioning the rationale. But if you go to Asaba now, you justify him. But then he was able to succeed because when he came up with the bill was so massive, so excessive, that if not that the governor understood what he was doing, if not that the governor is his friend maybe, and he was able to be carried along, the governor would have said, no, your design is off target or is off budget. So that is why it's a challenge for we engineers, right? Those of you that are civil engineers, you know you can build one-story building with Y16. Another engineer will use Y32. I mean, it doesn't mean that that one will fail, but it's just excessive. But you might question him, might query him. But when he now tells you that he's building a vault that will withstand a bomb blast, then maybe, and the thickness of the concrete of the wall is about maybe 750, just thickness. Or the depth of the beam is 1 meter, and the width is 500 mm. Then you begin to appreciate him. But before then, you might not really understand what he's doing. 1 minute, please. At these parameters of rainfall frequency is a determinant factor to know how your design will go, whether you're using 5 years, 10 years, but there's a table that will advise you, that will make a recommendation based on your design concepts as an engineer. If you want to design water, if you want to design storm, it's good that you ask your clients, how long do you want this thing to last? And you need to ask yourself, am I designing for normal drainage or am I designing against flooding? Am I designing against surcharge? That's what we call it. Surcharge, normal surcharge. Water is rainfall, the water is surcharging, and you need to control it with your drain. Or are you designing against flooding? That flooding that comes at the peak of rainy season, every 2 years, every 3 years, every 5 years, every 10 years, and so on and so forth. Okay, now there's a classification of rain. You might not understand this, but see it this way. We have weak rain, we have moderate rain, and we have heavy rain. Why are they moderate? How are they weak? It depends on their rainfall intensity. The higher the number, the heavier the rain. So this is what the IDF looks like. The duration of rain on the horizontal and intensity on the vertical. Then this line indicates the return period for 10 years, for 5 years, for 2 years, for 1 year. So you read it off against the appropriate year based on the return period you are choosing, which is a function of the safety factor or the high level of insurance of that area. So insurance have a way of influencing this. Rural areas always use low values for rural areas because if the rural areas are flooded, I mean, it's only the crops that are affected. But when you are designing for city centers, big cities, special cities, or where you have commercial activities, that in the event of rain, it will be disastrous, then you high your safety factor. So there are many, in the past, there are ways to estimate rainfall intensity. There's what we call Reynolds number that was used in the early 40s, right? The Reynolds number talks about the rainfall intensity is a function of the duration and frequency. And this is the formula for it. But then all these things inside this cell, we are now collapsed into what we call time factor. And that is this. The time factor simply means the rainfall intensity multiplied by the time factor will now give you the rainfall of that area. So, for instance, the rainfall intensity in Germany is chosen as between 90 to 130 liters per second per hectare. That's just how it is, right? Now, the rainfall factor after a while, was now collapsed into one single value called peak runoff. So instead of having this elongated formula, this complex formula you have here, what you now have is simply something that makes more sense. So this drifting, wetting, evapotranspiration, infiltration, depression, if you collapse all of them, they will give you what we call runoff coefficient. And it's a dimensionless constant. For instance, roof has a runoff coefficient of 0.95. Why is it 0.95 for roof? Almost 1. It means that every rain that falls on the roof, 95% of them will contribute to runoff. Whereas a gravel part has a runoff coefficient of between 50% and 30%. What it means is that if water falls on a gravel part, you know what we mean by gravel parts, where you put in stones and a gravel, normal gravel parts, not macadam, not asphalt, not normal sand, not normal sand, but a gravel part. That when water falls on it, only about 15 to 30% will flow on the surface. And that one that flows on the surface is known as the runoff. So it means that the degree of paving is either you call it the degree of paving or you call it the degree of the degree of impermeability. The degree of impermeability. So the impermeable surface is what contributes to runoff. So that's why roof is about 0.95, which is close to 1 or 100%. Because every water that falls on the roof of your house will just fall down. Only few will maybe evapotranspirate or wet the surface of the roof. So you can see why it is not 100%. One would have expected it to be 100%, but it cannot be 100% because there are bound to be losses. And that's exactly what you have here. Some will drift away, some will wet, some will the one that falls on trees, like green roof, will evapotranspirate. And then some, if it's on the surface, some will filtrate. In the case of gravel, a lot of them will filtrate. A lot of them will depress. There are only few 30 to 15% to contribute runoff. So this peak runoff depends on the percentage of impervious area. So I've used 3 words: impervious, impermeable, and paved. It also depends on the surface type. In other words, type of pavement. Then it also depends on the slope. The more slope, the more runoff. That's the common sense, right? The more slopey an area is, the more the runoff will increase. Then it also depends on rain intensity and duration. You cannot compare rainfall intensity of Abuja and Lagos. Lagos is about 150, 140 for a 5-10 years storm period. In Abuja is around 100 to 120. In Maiduguri is around 80. In Sokoto, maybe 90. And so on and so forth. So it depends on the weather condition, the area, the geography, and the meteorology of the area. Then finally, it also depends on the type of soil. The type of soil and vegetation. The type of soil and vegetation also have a role to play in estimating your runoff coefficient. Remember, we are talking hydrology, so there's nothing like SEWER here now. We're just talking about hydrology, and hydrology has to do with storm, rainfall, runoff, flooding, surface flow. Use any word you want. It all means urban drainage. Storm urban drainage. Now, the slope of a place affects the rate of runoff. So here, you could see the more slopey an area is, the more the runoff. For instance, for a slope less than 1%, and the impervious area, when I say the impervious area, it means the area that will not allow water to penetrate in, meaning that that area is the area contributing to runoff or contributing to discharge. If the impervious area is 60%, right, and the rainfall intensity is 130 liters per second per hectare, the discharge will be, the peak runoff coefficient will be 0.55. What this 0.55 means is to say that 55% of the area is what is contributing to runoff. 55% of the area is what is contributing to runoff. If the same area has a slope of 3%, then the peak runoff, or the amount of water that will produce from that catchment, will increase to 63%, which is about 8% increase. It means that anywhere you have a slopy valley-like area, expect problem at the downstream, because it means that water will come at a speed or at a high force. Now, this is a typical of how runoff forms. If I have my outlets here, and these are catchments or houses contributing to runoff, whether sewer or storm in this case, it's the same thing. The difference is that in the case of storm, this will be an open drainage, or it will be a big pipe of not less than 600 mm, between 600 mm and 1.2 meter. Whereas if it was to be sewer, then we're talking about underground 200 or 150 mm pipe. So these are the houses, these are the yards, these are the streets. So if runoff comes now, it will build up. That's just what this diagram is trying to show you. So by the time water falls here, if you have small flow here, by the time you get to this end, it's going to be a huge flow. Here is about, say, 1. Here is about, say, 5, a value of 5, increase of 5-fold increase. That is why it is people who are living on the downstream that will always be at the receiving end of the flood. People who are living on low areas, because water will flow from high areas to low areas. So by the time water gets to their place, it has percolated, it has aggregated, and it has considerably increased. If you have a question, just raise your hand, or you use the reaction icons. I will see it, the system will prompt me, and I will answer. So this is well understood. So this is sewer here, but it could also be open drain. It's the same principle, it's the same methodology, it's the same system of flow. Anything that flows follows the same concept. So, as I said in the past, runoff used in dimensioning is simply rainfall intensity times the time factor times the peak runoff, then times the catchment area. Remember the formula, the first formula I said, times the catchment area. So here you have location, which is rainfall intensity. You have rainfall frequency. Then you have the duration. So if you combine the frequency and the duration, you get the time factor. Then from your map, you can get the catchment area. Then your intensity, you get it based on location. Although now we have a chart, a chart for it. This is by the box. Then your catchment, slow catchment, your percentage of impervious area, and your rainfall intensity. All of them are influenced by your runoff coefficient. Is that okay? So that is that about stormwater runoff. Any question? If there's no question, we'll move away from hydrology. So So I'll rename this one Hydrology and storm. So that hydrology or stormwater, oh, it cannot change because I'm using it. So unless I close it. Okay, let me leave it for now. So let's move to hydraulics. Or let's move to the opposite, sanitary sewer. Any question? Please, can we talk? Any question? Are we all following?
And now on mute.
So we are back. Mute yourself once again. Now, let's talk about the other one, which is the sewer. So for the sewer, just like I said, wastewater sewage will be the wastewater flow, which is the daily water flow plus infiltration flow. What you have, this QD simply means daily water flow, daily wastewater flow. So wastewater flow is the daily demand or wastewater demand plus the infiltration flow. So the dry water flow is also defined as the wastewater flow, wastewater flow plus infiltration water. I've talked about it. In this case, we're not talking about specific wastewater production, which is liters per capita per day, like we did in water design, liters per capita per day. So the amount of wastewater production is a function of the quantity of water consumed per capita per day. Then you can also aggregate it to be liters per hectare per day. Why do we have liters per hectares? Because most times you might not be able to estimate the capita, the number of persons. So you use the land use. You talk about the land use, the catchment area, right? Then if you're talking about industry, then industry means you're no longer talking about individual, you're no longer talking about area, you're now talking about production unit. It will now be production unit. So for all production, is the amount of wastewater to generate a certain amount of goods. It's the amount of wastewater that you generate. So that increases as the product increases. Then you have the rainfall intensity or discharge rate. It's known as Q. So total discharge will be converted into any of these units, either to liter per second, meter cube per second, meter cube per hour, meter cube per day, or meter cube per run. So any of those parameters will serve. So this is just an example of domestic wastewater around the world. In domestic wastewater around the world, in terms of international comparison, right? In terms of liter per day, you could see that most European countries are on the average of 150, while countries like USA, Japan, they consume water a lot, even Canada, 250. I don't know why it's so, but that's just what it is. Germany is about 129 because they keep applying energy efficiency in their water system every day. Now, normally for wastewater production, it varies between 100 and 250 liters per capita per day. So anything between 100 and 250 liters per capita per day, you can use it. So, and it depends on the size of settlement, depends on the type of building, depends on the weight of the population. Nowadays, we normally use 130, right? And we can also take our design values from the table. So basically, if you now want to estimate your discharge for a 24 hours period, you simply multiply the population equivalent by the wastewater demand. So if each person is producing say 100 liters per capita per day, and there are about 100 persons, that means the wastewater flow will now be 100 times 100. That's just what here is talking about. So this is a case study of wastewater flow in Germany. 130 is the average. So you don't discharge, there are some rules that guide wastewater production or discharge in sewer. Number one, you don't allow constituents that destroy sewers to get into the sewer. You don't allow water or constituent that hampers the operation of the sewer system. You cannot start pouring acid or dangerous chemicals into your sewer system. It will damage it. Then you don't allow things like grease, oil, or chemicals that diminishes the treatment efficiency of the wastewater treatment plant. It's not allowed. You don't also allow discharge that will impair sludge treatment, basically organic contents, things that are non-biodegradable, like grease, oils, different types of it, petroleum. Those ones are dangerous because once most of them get into the wastewater treatment plant, they tend to affect the anaerobic bacteria. Then you don't allow things that endanger the health of the personnel. Don't go and start pouring acid or dangerous chemical into the public sewer. So these things must not be discharged. And this thing affects for waste. This includes waste, hardening substances, inflammable substances, oil and fats, toxic substances, detergents, disinfectants, animal feces, and vapor. It is dangerous to discharge chemicals into the wastewater treatment system. Please don't do it. If you do it, there's a possibility that it might get to the wastewater treatment plant and to kill all the bacteria that they have built over the years. You know that how wastewater is treated is that you get a number of bacteria, put them together, and they will start to feed on this wastewater that are already rich in organic content, right? So you see somebody culturing bacteria over the years, and then suddenly you just discharge something inside the whole thing, and the whole thing will just start from scratch again. In developed countries, I'm telling you, you'll be jailed if not prosecuted. So that is that. Now, this is just the opposite of what we did last time. Specific wastewater production. What wastewater production can you assign to different categories of houses, hotels, and everything? This list is inexhaustive. This list is just a guide. So for hospital, you assume 250 liters to 600 liters per person, per bed anyway. For swimming pool, you assume between 150 and 180. For school, you assume 20 liters per people. We know why it is 20, because they don't bathe, they don't cook, they don't do other things, they don't even wash, except for dormitories. When it comes to dormitories, you use the value for normal, normal systems, normal residential area. Then pulp production requires a lot of water. Paper production, very huge. Okay, in terms of tons, that is in terms of tonnage. Beer, the same thing, and so on and so forth. Textile, 40 to 20 meter cube per ton of products. Let's talk about infiltration water. As I said, infiltration water for sewer is a bit lower than the one for stormwater. So you can see this is the unit. You can just add this in addition to your value, right? Then in a separate system, it's almost 100% of wastewater flow. That's just it. Then in the combined system, it is between 30 to 40% of wastewater flow. and so on and so forth. This is not important. Okay, that's the end of that. Then last but not the least is hydraulics. Let's talk about the hydraulics. So please, I want you to bear with me. It's good that we lay a foundation, not just the foundation, but familiarize yourself with the topic and the terminologies that I use. Just like I always tell people, when you say you're a water engineer, you should use those terms. Sometimes I'm careful not to use the high-tech terms, but then I think I have a kind of a good reserve of those terminologies, and it's really cool. Now, general component of a sewer system for the hydraulics. For the sewer network, we have what we call gully inlets, we have the pipes, we have the manholes, we have the special buildings. So the special buildings can be in terms of the drop structures, the vital siphons, the overflow, and outfall structures. Outfall is where the stormwater enters the stream. Okay, you know, it's usually designed in a special way. Sometimes riprap, sometimes it's the biggest hole you can see. Then you also have valves. Then you have the pumping station, which you usually have at the treatment plants. In most sewer and stormwater design, flow is by gravity, except in exceptional cases, which is rare anyway. Then for stormwater tank, in the combined system, in the separate system, they have the infiltration structure. They have the wastewater treatment plant. So these are the components of the sewer system. Wastewater treatment plant, infiltration structure, they depend on the type and the size. It could be the swells, it could be the basins, filtration basins, it could be other things. Okay. Gully inlets. What is the objective of gully inlets? Is to collect surface water from streets and roads. It will reduce retention of sand, sludge. But we don't implement this anyway. We don't go to deseal our inlets. We don't do it. What we see is that after a while they'll block. Too bad. Then you have the waste. You have other things. Then discharge of stormwater into the stormwater and the combined systems. Then dimensioning. Gully inlets, this is how you dimension it. It takes a maximum area of 300 meters square. This should be more than 45 meters end to end from each other. And you should connect it with minimum of 150 mm pipe diameter. The construction has different standards. So this is what the gully inlet looks like, right? Then pipes. We have closed pipe, we have sedum ditches. This is for sewer. So sewer pipe must be closed. They must be closed. And the flow has to be from by gravity. It is not often that you have force pipes. It's just once in a while. Just like you don't normally use ditches. Ditches are old systems where they use ditches for wastewater. I mean, you see odor everywhere. You see mosquitoes everywhere. So it's not really ideal. Then there are different cross sections. You can have the circular profile. I have the egg shape. You can have the mouth shape. You can have the rectangular profile pipes. The choice of pipe determines is based on the amount of wastewater. The bigger the wastewater flow, the bigger the pipe size. It also depends on the slope of the sewer. It also depends on the variation of flow. It depends on the depth of what sewer. It depends on the static and dynamic loads. It also depends on how you want to operate and maintain the pipes. So this is a circular pipe. This is an egg-shaped pipe. And this is a mouth-shaped pipe. And of course, rectangular is something we already know how it looks like. So, open trench construction. These are some of the things you do. These are the advantage. It's independent of buildings. It does not interfere with traffic. Disadvantage is that it's very expensive. That's for tunneling. Then you can use shelling, you can use pipe, you can use micro tunnel and so on and so forth. I don't think we need all this. We really understand it. So this is milling into the ground. This is only used for small diameter pipes. So there are different sewer pipe materials. You can use clay, you can use concrete, you can use bricks, you can use pipe, plastic pipes. Plastic pipes are good because they are corrosion resistant, and you can apply good construction practice. Then you have other things about the pipe materials there. So sewer layouts. It is recommended that you use the shortest possible way. Then with the slope of the street, you can use the slope of the street, but suitable slope so that you avoid deposition. When you are talking about sewer, you must make sure that your slope is good. If you don't slope well, there will be blockage. There will be sediment deposition. And with time, it will build up and it will block the sewer parts. You should change the diameter only at manholes. Anyway, you change diameter and depth of depth, you are supposed to introduce a manhole. You don't do construction in flow direction. Sewers are meant to be dedicated right of way, to have dedicated right of way. So you should avoid backwater formation at higher road level, and so on and so forth. For sanitary sewers, in some countries, the minimum diameter is 250, but in our own case, there's 150, please. Then for stormwater and for combined sewers, the minimum you can see is 300. For me, it can even go up to 600, the minimum. These are minimum value. It can be as high as 1.2 meter. I just told us of somebody that did a stormwater sewer of 3 meters in Asaba. In Abuja, most of them are 1.5, 2 meters. I have seen them. Okay.
Please, what material can we reference for minimum slope?
You get it.
Okay.
Okay, so there are different ways you can arrange the sewer. You can arrange them in the main road. You can arrange them in narrow streets. You can arrange them with streets on building on one side, and so on and so forth. I think if you read this, you can understand it. You should not allow your sewer invert level to go below 2 to 3 meters. However, you have to also safeguard it against freezing. So water supply pipe should be laid above the level of the sewer, and so on and so forth. These are just safety measures that one need to take. So manholes are required for ventilation of the sewer system, for control and maintenance, and for cleaning of sewer. The arrangement of manhole should be arranged for accessibility. You should also introduce manhole if there's change in diameter, if there's change in pipe material, if there's change in slope, and if there's change in direction. These are the best of places to introduce manholes. So, and so on and so forth. So this is what a manhole will look like. You can see the concrete wall, you can see the entrance shaft, you can see the ceiling against filtration, and so on and so forth. This is a manhole. The pipe at the bottom, then with an embedment of maybe solid material. Then with riser steps built inside it, then with manhole cover, and then the entrance shaft. And then you also do some level of benching around the channel so that water will flow well.
Please, I have a question, please, from the previous slide.
Okay.
Yeah, so I want to know what should be the minimum height from the invert level of the pipe to the base of the manhole?
I think it depends on the depth of the pipe. The manhole is meant, the pipe is meant to pass through the manhole. For ordinary storm, depend on whether there is a other water system on top. But normally, within 1 meter, 1.2 meter is adequate. Because if it is less, it will be subject to, if your pipe is less than 600 mm from the surface, there's a problem, right? During road construction or during other things, people might just, it might be affected. And when you have a huge axle load coming from the surface of the road, they might also influence your pipe side, your pipe. So it's better you go at least 1.2 meter depth.
From the surface, right?
Yes, from the surface, exactly.
So does this apply also to domestic sewer lines or just for road?
The most domestic sewer lines. Yes. Well, this is domestic sewer line we're talking about. Yeah. You can see the pipe size is very small.
Yes, yes.
Yeah,
so
but the same principle applies to the other one.
Okay. So it should be a minimum of 1.5 from the surface.
No, I said between 1.2. There are other things that affects that. It's in the highway design manual. It depends on, is it over the road? Is it in a bush path? There are other factors. You can't
what I'm asking is within a compound. So when you have like a home environment within the compound or a large
600, 800 is even adequate because there's no overburden. There's not too much overburden, like car parking and heavy load.
Okay, so 600 from the surface.
Yeah.
All right. Thank you.
Okay, thank you. So this is just a pictorial example of what a storm sewer it looks like, which can also be big sewer flow, especially close to the treatment plant, because as the sewer is getting to the treatment plant, pipe size is getting bigger. But for me, this is a storm. This is for storm because it's a concrete. You hardly use concrete for sewer. So this is why is this manhole here, because there's a bend. Inspection chamber, we also have a inspection chamber. You need a inspection chamber for aeration, for access, for cleaning. Then you can also preserve as smaller manholes. So I think I've explained it before. Normally, for runoff, we expect your runoff velocity to be between.
Please, can you mute Engineer Ralph, please?
Okay, sir. So now, you could see that on the average of wastewater flow is between 1 and 2.5 meters per second. That's the average velocity flow. For the dry weather flow, it could be lower. While during runoff events, it could be as high as 6, right? Just in line with what we discussed last time. Your wastewater flow, your water flow should not be more than 3 meters per second. In the case of stormwater, it could be more because it's being controlled by flooding. But the dry water flow should not be less than 0.3. But here they're saying you should use an optimum. This is optimum value of 0.5 to 0.6. So this is basically optimum. Flow variation between stormwater runoff and the water flow could be as high as 50:1. So you could see that wastewater discharge is very small compared to stormwater flow. So this is sediment deposition. This is why we avoid, we ask you to make sure that this look very well. You can see that sediment is building up here. And over time, it will form what you don't know. Can even grow vegetation and block the sewer line. So I've explained this law of continuity, and that is the basics of pipe hydraulics. Velocity is discharge over area, right? Then there are losses. The losses is defined as this, right? Which is the length over the duration, over the diameter, sorry, and also a function of the velocity over 2g. So this is flow due to velocity, while this is the length and the depth, which talks about the wetting. So this is the general formula for losses, according to Weisbach. Then, according to Prandtl and Colebrook, this is what the frictional losses looks like, where K is the wall roughness. You can read it and understand it. This is like different types of runoff manhole that are applicable. So I think all these ones are just example of literal wear, different types of wear, different types of separations. So basically, this is like what we call stormwater overflow. Now, this is like a surface. When the water level here rises, what happens? The top clear water, the decanted water, will overflow. When it overflows here, it goes to a combined sewer overflow. It's more like a tank. In the developed world, they built a big tank so that excess water will flow into that tank, water that are not too diluted. Then immediately after this rainfall sink, they will discharge it into the treatment plant using the other bypass. So this is what it looks like. You see, normal water will be flowing here. As soon as the water gets to a certain level, it will overflow here. The same thing here. So this is a normal wastewater flow, well polluted. But once there's a storm event, the water level rises and then overflows here. So I've talked about outflow structure. These are those structures that will discharge water either to the treatment plant or to the open stream. Yes, they're the one that connects your design with the water bodies. And there are some things we need to guide during their construction. So this is what it looks like. So this is the physical one. This is an outflow structure that takes the wastewater, the unpolluted wastewater or the runoff, not sewer, allow it to join this river. Pumping station. Pumping stations are for wastewater facilities. That's just it, and especially the Catchment screw pump. So, or the sewage type of pump. That's what they use. So for wastewater pump, there are some conditions that are required of them. High operational safety, must be fast, automatic. It must have a robust construction. It must be non-sensitive towards pollutants and gross materials. So the pump should have a way of taking care of materials to avoid abrasion. So these are just like some of the basic things that we expect from a pump. It must have a low running cost. It shouldn't be expensive. It should be easy to repair. It should have replaceable parts. It should have high efficiency. So we have different types of pump using wastewater and stormwater. We have the rotary pumps. They are very good. You have the displacement pump. They also use, and then you have the screw conveyors. Screw conveyors are the one we call Catchment screw. I will show you what it looks like shortly. And it's often used, this is the most used in wastewater treatment plants because of the presence of non-dissolved suspended solid. So this is more like a rotary pump. It's what it looks like. It's still a rotary pump. This is an example of a rotary pump undergoing repairs. A big rotary pump, submersible, submerged and submersible. Then this is the technology, right? So you put the pump here, and then you pump it from here where you have valve. This is your manhole fittings or inspection chamber. You have the guider pillar to guide the wastewater. You have the motor of the wastewater at the center. Then you have some coupling to do, so you can attach it to the exit pipe. Then this is the wet well full of water, and this is the pumped. Then you have a small ventilation to the surface to make sure to take care of the odor and to treat it gradually. So for the rotary pump, can also run dry. So this is the dry arrangement. Remember, the other one is wet arrangement. The other one is embedded inside the manhole. This one is embedded inside the water. So water will cover it. So everything is inside the water. But in this case, there's a compartment for it, different from where the water is. So the water will full here, enter here, and to pump it out. So this is the dry arrangement, where the other one is the wet arrangement. The other parameters remains the same. So here you have the motor, not protected, because there is no possibility of water coming in. So this is an example of a horizontal screw pump, or they call it displacement pump. So these advantages of that, this is what the Catchment screw look like. The flow rate, the inflow, the cross section. These are the advantage of screw pump. Please, if you are dealing on the wastewater sector or you are designing wastewater treatment plants, this is inevitable. You must need this type of pump. The reason is that the water flow, when you design your wastewater, you design by gravity. So for the water to get to the treatment plant, it's going to arrive at the treatment plant at the lowest level. It's more likely arrive at the lowest level at the treatment plant. So you have to now lift it up back. Like in Whooper, the difference in elevation between city center and the treatment plant we have in Abuja is about 12 meters. Some can go as high as 18 meters. Then you now need to pump it back to the level of the treatment plant. Meanwhile, every treatment plant is usually located at the lowest level. That one is there. It's usually located at the lowest level. That one is constant. All right. So this is what it looks like physically. Why is it 3 a number? Can somebody tell me? Why do they have 3 of it? Can I get the response? Why are they 3 of it? Why not 1? Well, any question, any response, you can put in the chat box. There are 3 of them. Probably they need only 2, but you have to provide 3 in case of breakdown. And then you cannot say 1. So most times there's peak period and there's non-peak period. So during peak period, 3 of them will come on stream, or 2 of them will come on stream. During non-peak, 1 will only come. So this is how you rate efficiency of wastewater pump. So every wastewater pump has high or low efficiency, right? So the screw pumps are performing best, while the screw and the propeller pumps are the perfect pump you can use. Conveyor is also good. Displacement pump are also good, and so on and so forth. But pneumatic lifting equipment is poor. The rotary pumps that have spiral casing are usually not too good too. So require head. So here you see head 1, head 2. So I'm delivering water from here to here, right? So these losses, additional heads, ideally my head should be H2, but because of frictional losses, my head will now be added. So that is how you get losses due to suction. So sometimes you have a losses suction loss. You have a suction loss, which must be covered by the pump. This is something that requires further reading, and we'll definitely understand it. So here you have system characteristics, which is just, if you want to talk about the total head is comprises of the geodetic head plus the hydrostatic head, then plus dynamic head, which varies due to flow in velocity. The hydraulic geodetic head is simply H1 over H2, which is difference in head, two heads, while the hydrostatic head is difference in pressure. Then dynamic head is the difference in discharge, or the changes in discharge or dynamic discharge. So these are the type of three heads losses that can experience in any pipe network or any pipe system. The geodetic head due to difference in head, the head due to the friction, due to the pressure changes, and then the head due to the flow of velocity. The higher the velocity, the higher the losses in terms of the roughness, the efficiency of the pipe. Then every pump has what they call the operating pump, right? Which is a function of the system characteristics and the pump characteristics. So there's a place where the head and the discharge of a pump are optimized. That is called the operating pump of a curve of a pump. Operating pump point of a pump. Okay, that is the end of that. So we'll go back to our folder now. So we have treated all our course materials, and that is the foundation for this course. Please, I want to encourage you, if you have time, you can go back and study these materials. You see our speeding. Then I've also introduced us to the design, highway design manual that detail all the rainfall intensity all over the country based on the state. If you don't find your state, you interpolate with the state ahead of you and below you. If you're in Abia and Imo State is 150 and River State is 130, then you should choose 140, that kind of thing. That is the rainfall intensity duration curve. You can go and take a look at it. The horizontal is the duration, be it minutes in hours, doesn't matter. Then the vertical is the rainfall intensity in millimeter per hour. And then the horizontal or the diagonal is the return period. Okay. So that is now the next thing I would like us to look into before we meet next week, this is today just for foundation, is to look at we'll be talking about rational method throughout next week. Focus on the rational method. That'll be our focus for next week. So what I'll give us assignment. This is the assignment. I want you to develop an Excel sheet and let it look like this. You see chart of rational method. So here you have pipe. This rational method is combined. Between here and here is the wastewater. From here is the stormwater. Then this is the slope. This is the wet area. This is the diameter, which we are looking for. And all of us are entering the water. We're not going to have a problem with this. So the assignment I'm giving you is I want you to go to Google and look for templates or charts of rational method in Excel. If you can't find one, then try to build one. Forget about these values. I'm not interested in all these values, but I'm interested in these headings. This place is area, catchment, subcatchment area. This place is wastewater, this 2 cell. And the wastewater is catchment area multiplied by the dry weather flow. This one is the summation of dry weather flow. This one is, when you come to storm, this one is peak runoff coefficient. This is impervious area. you can see, I've shared it a lot of times that the color has faded. So this is impervious area. This is summation of impervious area. This is time of estimated time. This is summation of estimated time. This is the duration here in minutes. This is seconds, hectares, liter per seconds, hectares, number. Then this one is RD_N, R_DN, which is rainfall intensity, a function of duration and frequency. So I want you to go online and develop and search for templates. There are many of them. That's why I want you to do that. And it's also a way of encouraging you to learn to search for templates that you need online. So if I say templates, okay, let me end the recording.